Okay, people, so today we shall move on to do something on forces. Last lesson we went on to list down all the forces. There are like 8 to 9 of them, I remember, and then we went to frictional force, yeah, in details. And today we are going to go on to something very important. Personally, I feel that it is more important than F equals to MA and F equals to dP dt, because usually Singaporean students or our international friends don't have much of a problem solving equations. The problem is really representing and understanding the problem. That is the key. If you can understand the problem, represent the problem properly, solving equations is never a big issue for our students. So today we'll focus on understanding forces acting on bodies, and this is really crucial. Before I go into the drawing of forces on bodies, I need to go through this very important, but simple but very important and powerful law that Newton mentioned a long time ago, which is Newton's third law of motion. It is more relevant to what I'm going to do today, so that's why I'm going through this first. Anyone, in your own impression, what's the Newton's third law? Come on, you must have heard of Newton's third law, right? So what's the Newton's third law you have heard of? For every action, there's an equal and opposite reaction. For every action, there is an equal and opposite reaction. Okay. Now let's use this third law and see whether it makes sense. Yeah. So if I got an object over here, there is a normal contact force, there is a weight over here. So are they action-reaction force? Yeah, equal. They're opposite. So what's the problem? Yeah, we are the same type. And there's a very important rule that it violates over here. Let's take a look at this. Normal contact force acts on, in this picture over here, the normal contact force acts on the box, right? I mean the box, yeah. So the weight acts on the box as well. So the two forces act on the same body, and this cannot be solved for Newton's third law, the action-reaction force. One very important rule other than equal, opposite, just now we mentioned that must be the same type, which is a good point, and it must be on different bodies. It must be on different bodies. Can you see that if the action-reaction force acts on the same body, then nothing will move in this ball. Exert a force F on the box, and then the box suddenly experiences a force F backwards, and then nothing will move. Yeah, we wouldn't be able to make it to circulate. So, is this complete? Not that complete, yeah? So let's have a revised version. And the revised version is what you really need to remember, that an object A exerts a force on B, and B exerts an equal and opposite force on A. So what is missing in the first definition? It's fine, we learned from it. We need to know what is missing. What is missing over here is, what's missing? Between this and this. Yes, exactly the idea about different objects. And it's not just on different objects. It's object A on B and B on A. It is not A on B and B on C. Yeah, it must be between the two bodies. This is very important. Yeah. So let's apply this idea back to the same example that we did just now. So if we have the Earth, it's a bit too small. If we have the Earth and the box. Now, we know that there are two forces acting on the box. Now, which is the action-reaction pair of normal contact force on the box? We see that when A exerts a force on B, B will exert a force on A, right? So if the box experiences normal contact force by the Earth on the box, therefore the reaction force will be the normal contact force by the, no, this is already by the Earth on the box. By the box on the Earth, yes, right. So this is by Earth on box. This will be by box on Earth. Then what is the reaction force on weight? By, this is by Earth on box, Earth on the box, and the box on the Earth, yes, right. So why is it that if you, it is a little bit weird to ask, why is it that if you jump off the building, okay, let's go for a healthy example. If you do bungee jump, if you do bungee jump, why is it that the Earth doesn't come to you? actually, if you are like Thanos, if you have the whatever stone, I don't know what stone you have, yeah, the Infinity War, if you have the don't know what stone, you pull the planet towards you, actually the planet that you're on will move towards the other planet. So one day if Moon were to fall towards Earth, the Earth will move towards you. Yeah, because your mass is very, very small compared to the Earth's mass, that's why it doesn't move. Now even if you ask all the people in the world, since we are on this topic, if you ask all the people in the world to stand on one side and then jump up, will the Earth actually move in the opposite direction significantly? Hey, come on. Settle down, quick. We are going through something important. Just don't take up the front row. Yeah. You can take the second row then. For some reasons, the camera has some housing force. Okay, so if you ask everyone in the Earth to come over here and then jump, will the Earth be pushed to one side? Okay, the mass of an average person say about 60 kg. Okay, let's say 60 kg. How many people are there in this world? 60 kg times 7 billion people? 7? Yeah, so 7 times 10 to the power of 9, which is about 42, so about 4.2 times 10 to the power of 11. Yeah, this is the amount of kg that we're talking about. The mass of Earth is 10 to the power 30 is the sun. The mass of the Earth is 10 to the power 24 kg. So there is still a difference of 10 to the power 13 times. So even if we ask everyone to stand on one side and then it doesn't affect. Even if you detonate all the nuclear weapons on one side, it still doesn't affect. It does probably. Yeah? Yeah? So it is actually just talking about scale over here. Now, let's use this idea that we have developed of reaction force on a more typical example that students will always have problems with. I hope that you won't face the problem, but let's see whether we have this issue. So let's see if we place a person in the lift and the lift is accelerating upwards. Yeah? Now let's consider what I'm going to do right now is called a free body diagram. Yeah? Free body diagram. Now there is nothing rocket science about this. This is just drawing the forces on the person and the force on the lift. That's all. Literally you free the bodies from each other so that there's greater clarity on the forces acting on each body. That's all. Okay? So it's nothing really rocket science. So let's consider the forces acting on the men or women. What are the forces acting on? The weight of the person, the man, and the acceleration. Is it a force?
The
Normal contact force. Excellent. So normal contact force of the person. Now on the lift, there is obviously a tension force. What else? Weight of the lift and weight of the man. You sure it's the weight of the man? Now think carefully. The weight of the man acts on the man or on the lift. The weight of the man acts is an interaction between the earth and the man. Does it have anything to do with the lift? No, exactly. So the force that acts on the lift, to know which is the force that acts on the lift, let's take a look at what is the force that the lift acts on the man. So what's the force that the lift acts on the man? Which force? Normal contact force, exactly. So if this is the force that the lift acts on the person, what is the force that the person exerts on the lift? Is it his weight or the normal contact force? Excellent. So it is the normal contact force. This is the one that always gives problem. You must be very careful. The force that the person exerts on the lift is the normal contact force. Now this gives a very interesting outcome, which means that as the lift accelerates upwards, it is possible for the normal contact force to change. Which makes sense. Yeah? Because if I were to have a person accelerating upwards, do you agree that N has to be bigger than W? Make sense? Yeah, so that the person has a net force to accelerate upwards. Which means that N can change, even though W doesn't change. And that's why if you actually stand on a scale and if you're on the lift, and the lift accelerates up or down, the reading on the scale actually changes. Cool? You still okay with this idea? Okay, the key idea that I want to tell you over here is this is never the problem. This one is the issue. Be very clear that it is a normal contact force by the man on the lift. Okay? Now, let's enhance clarity by solving a problem. Yeah, let's enhance clarity by solving a problem. Because until you solve a problem, you will never have a good grasp of whether you know or not. Yeah, so let's give numbers. using this context over here and see whether you can solve the question. So exactly the same thing, and I've got an acceleration of 2 meters per second squared. The mass of the man is equal to 80 kg. The mass of the lift is 120 kg. I'd like you to draw, actually the forces are drawn already, using F net equals to NA, which is what you have learned in secondary school. Write an equation for first the man, second for the lift, and then use it to solve for the tension and the normal contact force. Give it a try. If you can look at the board, there are 2 questions I'm going to ask you before I go on further. Why do I take M minus W and not K minus N?
Because N is greater than W.
Yeah. How do you know that N is greater than W? Because the acceleration is upward, yes, correct. So you always take the direction of acceleration as the positive direction. That will always ensure that your this side will be positive. Because if you had taken downwards to be positive, yes, you can write W minus N, then you end up with a nasty negative NA over here, which is actually not that easy. So that's why I wrote N minus W. Likewise, that's why I take T minus N minus W. Yeah. Taking the direction of acceleration to be upwards as the system. Alright? Now, why do you think I put W, M, and WL? Why don't I just put W? Because they're different exactly, and when during exam condition, it is highly likely that under stressful condition, you might just substitute the wrong mass into the wrong equation. So it is always very good for you to actually have this kind of naming system so that you don't confuse yourself. Okay? So if you put in numbers, it will be N minus the mass of N is 80 times G equals to 80A. T minus N, which is unknown, minus 120 or 100. 120 G equals to 120 A. And A is 2. So therefore, this will give me N equals to 80 times 11.81. And you get a number. Then plugging this into the T, you get your answer as 11.81 plus 80 times 11.81, which is equals to 200 times 11.81. And you get an answer. Okay. So if you plug in all the numbers, you get an answer.
just say that T is 2,400 by taking the whole diagram.
Excellent point. You can actually consider, you can apply F equals to ma for this case, or you can apply F equals to ma for this case, or you can apply F equals to ma for the two combined. Now when you combine the two, you combine these two over here, the free body diagram or the force diagram that you will need to draw is WL, WN. Now you're combining the two together, and then this is A. Why is it that N is not in this picture? They cancel, exactly. Because it's upwards and downwards, they are equal and opposite, so they cancel. Yeah. So this is also one way. So there are three ways of saying, and your syllabus will always only have two objects. So there are always three ways that you write it. Okay? So either one. You can use either two to solve for the unknowns, and then use the third one to check whether the equation is correct. Okay? Because if your values are wrong, then the third equation will tell you that it cannot, it doesn't satisfy. Cool. So three equations, use two to solve. 2 point. Excellent point. Now with this, I'm going to give you one example to show you why is it that F equals to ma is incomplete. In the next lesson, I'm going to follow up with more examples so that you can practice this, but I'd like to just give you something to think about before I move on to the practical. So let's take a look. This is my favorite example. Imagine you've got a conveyor belt. Yeah, you've got a conveyor belt that is pulled towards the right at constant speed, and you drop sand onto the conveyor belt. Do you agree that if I were not to exert a force, or rather, if I don't exert a force towards the right, if I drop sand onto here, what do you think will happen to the belt? If it is on constant speed. If it has speed v, and I drop sand onto it, what will happen to the speed if it is just you decrease? Excellent, exactly. Yeah, so you slow down. So in order for it to be at constant speed, do you agree that I need to exert a force? Now this is where the dilemma comes in. You remember that F equals to ma. Now what is the acceleration of this case? The belt is, so what's the acceleration? So this is 0, so it equals to 0. So is F equals to 0 or F is not equals to 0? We know common sense tells us that you need a force, right? But why is it that the equation tells us that F is actually equals to 0? So can you see that there's some dissonance over here between the prediction and the actual situation? So there is some incompleteness in F equals to ma.
So isn't it the whole equation is only equal to use the mass?
Excellent point. Yes, correct. This is assuming the mass of the belt is constant, but the mass of the belt is not constant. So how do we factor that the n dt part of this equation into this equation? The n dt part of this equation into the equation. So this is what I'm going to touch on in the next lesson. Okay? So have that linger in your mind. In fact, you can find the answer in your notes. So read it out before you come for the next lesson. In the next lesson, I'm going to go through more examples so you can apply F equals to ma, and I'm going to go through the more complete interpretation of Newton's law and force. Cool. Yeah. And if the time is opportune, if you are ready, if I feel that you're ready, then I'll show you how integral can be, introduced again. Cool? Yeah. So I will stop this part here. So I can record another